Thank you, OLLI and the library, for having me here today. All right, before I jump into the talk for today, I just have a little plug for the Central Oregon Geoscience Society. I think that many of you here are aware of this organization, but if you're not, this is just a screenshot of our website, of the homepage of our website. So if you're interested in geology, and you must be at least a little bit interested in geology if you're here today, then check this group out, because we do talks once a month, always on the fourth Tuesday of the month, and we bring in speakers from universities, agencies, just a whole range of researchers who are working on all aspects of Oregon and Pacific Northwest geology. So our next talk is on Tuesday, and it's on sunstones. We'll have Emily Cahoon from Oregon State University, and also some of her undergraduate students who have all been working on different aspects of sunstones. Those talks are always free and open to the public, and we meet at Bridge 99 Brewery. They're also in Zoom, so you can just go to our website, click on this, and it'll take you to a Zoom page where you can register for the Zoom meeting. We also do field trips. You do have to be a member to go on the field trips, but everything else is free and open to everyone. And then we also support research. We give grants to graduate students and undergraduate students who are working on any aspect of earth science in Oregon. So if you know anyone who's doing that, let them know, because our grant cycle will be starting up at the beginning of next year. And then we do outreach at K through 12 schools. So just another group to be aware of if you're interested in geology. All right, so with that, an overview of what we're going to talk about today. We're going to be kind of taking a broad look at global geologic forces, plate tectonics mostly. Don't worry, I think they're working on that. And then we're going to sort of be big picture geology and then zoom into what that means for Oregon. So we'll start with an overview of plate tectonics, and then we'll look in detail at subduction zones, continental rifting, and hotspots, all part of plate tectonics, and then how those tectonic forces have shaped Oregon's high desert. And then what does this look like in terms of the landscapes that we see as we're out and about in Central Oregon and beyond? We'll move all the way through Eastern Oregon as well in some of the photos that we look at. Okay, so to get started, this is a map of Oregon. It's a fairly old map. It's been around for many decades. And these geologic provinces of Oregon were recognized since the very first geologic maps of the state were made. So this breaks the state up into, we're here, but you can see this green as the high Cascades, the Western Cascades, the Willamette Valley kind of smushed in between the Cascades and the Coast Range, the Klamath Mountains, and then on the east side of the state, the Columbia Plateau, Blue Mountains, High Lava Plains, Oahe Uplands, and Basin and Range. And we're here in Central Oregon, we're at a really interesting place geologically, because we're right where three of these geologic provinces come together: Basin and Range, High Lava Plains, and the High Cascades. So this map is something that we've had for many decades, but more recently, how many of you are familiar with maps like this? Bioregions or ecoregions of the state. So this is a more recent map, and if I toggle back and forth between, sorry, I have to do it there, this map and this map, some of those areas are on both. If you see in this map, if we look at the Blue Mountains area, there it is in the geologic map. The Cascades show up, obviously, and then there's the Cascades again in the geologic map, the Coast Range. So the geology of Oregon really shapes these bioregions. And these are called ecoregions or bioregions. It's just exactly what it sounds like. This is a map that kind of divides the state up into what types of plants and animals are found in that area. What is the ecology of that area? So the ecology of each area, you can see, is really shaped by geology. So geology shapes much of Oregon, and that's kind of just what we'll be focusing on today. All right, so let's jump into plate tectonics. So this is a map that shows plates on the planet. If you think of the Earth, and it's divided into layers. There's the core and the mantle, and then the crust of the Earth is broken up into these plates. And the plates are brittle. They're made of rock that is brittle. And if you have brittle rock on a round planet, then it has to be broken up into pieces or it wouldn't fit on a round planet. So those pieces are what we see here in these. The yellow are boundaries between plates. So I've just outlined the Pacific plate. And here is the North American plate. And North America, no surprise, sits on top of the North American plate. But the North American plate also extends out into the middle of the Atlantic Ocean. So they roughly match continents, but not totally match continents. So the entire crust of the Earth is broken into these plates, and these plates are in constant motion. And the arrows on the map are vector arrows. That means that they're showing not just the direction of movement of the plate, but also the rate of movement. So if you see an arrow this long, that represents about 10 centimeters of movement per year. And in geology, oftentimes we're just talking about these time scales or numbers that are just like enormous. They're really hard for human brains to really comprehend, millions or billions of years. But 10 centimeters per year, that we can comprehend that. That's a rate that is on a human time scale. And so as we're sitting here on the surface of the Earth, running around doing all of our busy human things, we're moving around on these plates on time scales that we can really comprehend. So the Pacific plate is an arrow about that long, about the one here. So it's moving about 10 centimeters per year. Other plates like the North American plate are moving much, much slower. So the arrows are letting you know not just the direction of movement. The Pacific plate is moving east and a little north. The North American plate is moving west, but also a little south. So the arrows are telling you not just the direction, but also the rate. So different plates, you can see if you look across the globe at all these different plates, some are moving very, very quickly, some are moving much slower. And that's just the movement of the plates in general. If you think of like on a cold winter day, sometimes the river in the Muir Pond area will freeze. And there'll be like a layer of ice on there, but the river below is moving. And those slabs of ice are moving. Different slabs are moving at different rates. That has to do with the rate of the river moving underneath, but it also has to do with how those slabs are interacting with each other. And so why do different plates move at different rates? The big picture is just they're all impacted by each other, and they're impacted by what's going on underneath them in the mantle. But for each individual plate, it's a different answer for why they're moving at different rates. Hopefully that answered your question. They're all affected by each other, and they're all affected by the movement within the Earth. There is movement in the mantle. The mantle is in constant motion. It's very slow motion, but it is motion. All right, so this plate tectonics explains how and why the geologic provinces of Oregon exist. So we're going to zoom into this little guy here, which if an arrow was put on top of that plate, it would kind of cover up the whole plate because it's such a small little plate. And so even though there's no arrow there, that plate is moving. Anyone know the name of that plate? Excellent. You guys are like going to do so well on the test at the end of this talk. All right, so that's the Juan de Fuca plate. And it is moving towards North America. Those two are on a collision course. So we're going to zoom into that little Juan de Fuca plate, and we're going to be talking quite a bit about what the Juan de Fuca plate is doing now and what it has done in the past throughout this talk. So kind of get a picture of what that little yellow line looks like right there, and then in this next slide, we'll jump in, in another slide, one more slide, we'll jump into that Juan de Fuca plate, look at it in a little more detail. But first, just kind of an overview of the types of movements that can occur at plate boundaries. So convergent plate, we talked about the Juan de Fuca plate is moving towards the North American plate. That's a convergent plate boundary, two plates moving towards each other. Plates can also move away from each other, divergent plate boundaries. And this image here is actually drawn more or less for our part of the world. So this is kind of representing North America here, and the Juan de Fuca plate subducting underneath the west coast of Oregon and Washington and Northern California and Southern British Columbia. So you can kind of think of it, it's not drawn perfectly, but you can kind of think of this as us, kind of on the east side of the Cascades. And if you go out further west under the Pacific Ocean, there is a divergent plate boundary where the Juan de Fuca plate is moving away from the Pacific plate. And then the Pacific plate is this huge plate that goes all the way across the Pacific to like Japan. And then there's another subduction zone, and that causes the volcanoes and earthquakes that occur in Japan. So divergent plate boundaries are where two plates are moving away from each other. Transform plate boundaries are where plates are sliding past each other. Think about like the San Andreas Fault in California. And then hotspots, and we'll get to hotspots a little later. Hotspots are not a type of plate boundary. Hotspots are just where more material is coming up and the plate is moving over the top, but they're important large-scale tectonic features. And so we talk about them when we talk about plate tectonics. Okay, so I promised that we would dive in here to the Juan de Fuca plate, and now let's do that. Oops, I didn't have to go back. I was more prepared than I thought. So there it is. There's the Juan de Fuca plate. There's that yellow line. Now it's black. That's the divergent plate boundary that separates the Juan de Fuca plate from the Pacific plate. Everything to the left of that line is the Pacific plate, and everything to the right of that line is the Juan de Fuca plate. And then this line separates the Juan de Fuca plate from the North American plate. So where those plates touch is actually offshore from Oregon and the rest of the Pacific Northwest. Here's the coastline. And you have to go out a couple hundred miles into the Pacific Ocean before you're over the area where the two plates are touching. And the little triangles on that line are, you can kind of think of them as teeth or arrows that are pointing in the direction of the plate moving down into the earth. This is a two-dimensional image. This is a map shown in 2 dimensions, but it's trying to relay 3-dimensional ideas. And so that's just a map symbol that's telling you this plate here is moving underneath the plate that's on top of it. So this is a subduction zone. And the subduction of the Juan de Fuca plate beneath the North American plate creates a linear range of volcanoes parallel to the subduction zone. So there are the volcanoes. And the black indicates actual volcanic peaks like Mount Hood and Mount Jefferson and the Three Sisters and Newberry volcano. But the red indicates all of the material that has been erupted by those volcanoes. So the black is just labeling. Was there a question?
I just wondering what the one at the bottom is, LVC.
That's Lassen. Yeah, Lassen Volcanic Center.
MS and MLV.
Let's see. So we have Lassen, Mount Shasta, Medicine Lake volcano. We'll just do them all. Mount McLaughlin, Crater Lake, Newberry. Already did Three Sisters, Mount Jefferson, Mount Hood. Let's see. What do we? Mount St. Helens, Mount Adams.
Lassen isn't south of Mount Shasta.
Yeah, Lassen is south. Lassen is the farthest south of the Cascade volcanoes. Simcoe Volcanic Field is that SVF. Mount Rainier, Glacier Peak, Mount Baker, and then I hate it when when people like draw the line at a national border and pretend there's no volcanoes up there. But I'm gonna actually have to be testing myself to remember the names of those Canadian Cascade volcanoes. Can anyone help me out with that? Fail. Yeah, Garibaldi is probably MG. Mount Garibaldi. I apologize. I'm disappointed in myself. Sorry, Canadians. They would not do that to us. All right, so that's the Cascade Range. Notice that the red, so those are just the major peaks, but there are hundreds and hundreds and hundreds of much smaller volcanoes that aren't labeled in there. And that's kind of represented by the red. So the red is like all the material that all of the Cascade volcanoes have produced. And notice that the Central Oregon section of the Cascades is really the most active section of the Cascade volcanoes. So you can kind of keep that in the back of your mind as we talk about the rest of what we see in Oregon.
It's Mount Meager.
Mount Meager, yeah, that's great. So that's MM, and then someone else can.
Mount Meager and Silver Throne Mountain.
Yeah, Silver Throne.
I'm
not sure if that's part of the Cascades. This will be a little piece of trivia that might be solved by the end of the talk. All right, so in the next image, this is a map view, and in the next image, we're going to kind of we're going to go into this area right here, and we're going to look at that area in a cross-section view. So now we're seeing what's happening at depth underneath us. So this is as if someone took a big giant knife and cut east-west through the Cascades and through Portland and through the coast and exposed what's going on beneath us. So there's the Juan de Fuca plate subducting underneath the North American plate. It continues out here into the Pacific Ocean. There's that place offshore where they touch. That's just that map view or that map symbol showing subduction that I just sort of slapped onto the top of this image. Just so we can see that we would have to, if we were going to go out to the place where the plates actually touch, we would actually have to be offshore a little bit. And here's the range of volcanoes that are created parallel to the subduction zone. So again, this is a two-dimensional image that is demonstrating three-dimensional processes. So you have to imagine that this slab of the subducting Juan de Fuca plate comes out of the screen towards you and goes into the screen. It's a big three-dimensional slab of material that's subducting everywhere along this entire boundary. And so everywhere along that entire boundary, there are Cascade volcanoes, not just Mount Hood and the volcanoes that we see here. So that explains the Cascades. And the reason for that is that when that subducting Juan de Fuca plate gets deep enough, it's about 60 to 70 miles below us. So as we're standing here or sitting here, and I'm standing here in this room, beneath us, 60 or 70 miles, there is the Juan de Fuca plate. And that rock in the Juan de Fuca plate has minerals in it that when those minerals get exposed to high pressure and high temperature, chemical reactions occur and hydrogen and oxygen is released from the minerals. So in this image, it says water is driven from the plate. It isn't liquid water the way we think of water. The pressure and the temperature are too great down there, but there is hydrogen and oxygen that is released from the minerals of the rock in this plate, and that gets into the mantle, and that causes the mantle to melt, and that molten material rises up and feeds volcanoes. Contrary to all of these images are always drawn for the mantle. This is the asthenosphere is part of the mantle. This is the mantle. This is all crust, but that's all mantle. The mantle is always drawn in red and orange colors in these images, which kind of makes you think it's molten, and it's not. It's solid. It only melts in very particular locations, and one location is at subduction zones, and that's because water, hydrogen and oxygen enters the mantle, and it changes the melting temperature. It allows it to melt. All right, so magma is produced, magma rises up, and that feeds volcanoes. So that's why we have the Cascade volcanoes here. It's because of subduction. Also here, there's a problem in that these plates where they're touching, they're locked. So the Juan de Fuca plate out here, if I back up one more, all this section of the Juan de Fuca plate from the divergent plate boundary here, where that plate is created at the boundary between the Pacific plate and the Juan de Fuca plate, the Juan de Fuca plate is moving here. It's moving towards North America. And so that's out here, movement. And the Juan de Fuca plate is moving here. It's moving down into the mantle. So there's movement here and there's movement here, but right where the two plates are touching, they're locked. And that is not a good situation in terms of things like earthquakes. This is not an earthquake. This is a tsunami. But because those plates are locked, and there's movement out here and there's movement down here, stress is building up in that location. And as stress builds up and builds up and builds up, eventually it will be released. And so the Cascadia subduction zone is capable of producing the largest earthquakes on Earth, magnitude 8 to magnitude 9 earthquakes. And because it is there's the subduction zone, because it's located underwater, that would then generate a tsunami. So earthquakes and tsunamis are something that we can expect here in the Pacific Northwest. This is the 2011 tsunami in Japan. Very similar subduction zone, very similar, like everything that we just talked about for North America and the Juan de Fuca plate could apply to Japan and is the reason that this earthquake and tsunami occurred. The main difference between our situation in the Pacific Northwest and the situation in Japan is far more prepared for these types of events than we are. So we have some work to do to be ready for this. All right, so this is not a talk about earthquakes or tsunamis, so we'll just leave that there and just go back to our much safer volcanoes. Okay, so this is the reason the Cascades exist, and it is also the reason why there have been other versions of the Cascades in Oregon. So now we're going to take a nice little field trip. I kind of have this talk divided up into different types of plate boundaries, how they've impacted Oregon. And then we go out and we look at places in Oregon where you can see this. And a lot of these images, if you're familiar with the Oregon Natural Desert Association, they put out a calendar every year. They have gorgeous photos from local photographers. And so these are almost every photo in here is probably at some point from an ONDA calendar. So these are all local photographers who have taken beautiful photos of our state. All right, so we're going to look at places around the state where we can see either the Cascade volcanoes themselves or an older version of the Cascades. This subduction process has been happening for millions of years off the coast of Oregon, and it hasn't just produced the Cascades. It also produced volcanoes in what is now the Ochoco area. So these are remnants of volcanoes. We're looking at very eroded volcanoes here. So just like kind of the old remnants of ancient volcanoes, they're kind of lumped together as the Clarno Formation. And throughout parts of Oregon, you can find rocks that are at the age of the Clarno Formation, which is about 54 million years to 39 million years. And this represents subduction from about 50 million, 55 million years, something like that. So an ancient subduction zone. So this is in the Spring Basin Wilderness. And today those volcanoes are recognized just by the volcanic rocks. We're not actually looking at like the base of a volcano here or anything like that. Too much erosion has occurred for us to see the original volcanoes. But we can see the volcanic rocks in these areas. So these are all remnants of an ancient subduction zone. And then the John Day Formation is sort of the next youngest version of volcanism produced by subduction. So this is in the Sutton Mountain Wilderness area. This is near the Painted Hills unit of the John Day Fossil Beds National Monument. Sutton Mountain is just to the north, but there are some outcrops there of some of those, colors that the Painted Hills are really famous for. And that's volcanic ash that was produced during subduction zone volcanics, 39 maybe to 18 million years ago. So if we go east of Bend, kind of northeast of Bend, but also southeast as well, we can see these remnants of ancient subduction zones. And then if we move a little closer to Central Oregon, the Deschutes Formation represents rocks from the Cascade volcanoes. So now we're in the Cascades. We're not in an ancient version of a subduction zone volcanic range. We're in the Cascades, but older Cascades than what we know and love today. So about 7.5 to 4 million years ago. At this time in the Cascades, there were no Three Sisters. There was no Broken Top. There was no Newberry volcano. All the Mount Bachelor, none of those volcanoes were there. But there were other volcanoes in the Cascades that acted in much the same way that these volcanoes today act. And they produce volcanic rocks that now we can see in the canyons of Central Oregon, like Waichus Creek and Deschutes Canyon and Crooked River Canyon. Those are all exposing rocks that are kind of lumped together in this name, the Deschutes Formation, and they all represent volcanic activity about 7.5 to 4 million years ago. And then, of course, we can see much younger rocks, more or less on the surface. We don't need canyons to expose them. And those are from the volcanoes that we know today. So this is the Badlands, just east of Bend on Highway 20, the Oregon Badlands. And those are all basalt lava flows from Newberry volcano. And Newberry itself is about 400,000 years old. These rocks are younger than that. I think they're about 80,000 years. But Newberry itself has been around for almost 500,000 years, pumping out lava flows and other volcanic materials like obsidian. This is the most recent eruption at Newberry volcano. So it's been erupting for roughly 500,000 years, but its last eruption, does anyone know when the big obsidian flow was formed? 1,300 years ago, which is very, very recent. So Newberry is definitely an active volcano. So when I say it's 400,000 years ago to present, geologically, it is really very young. It is still active and it is still capable of erupting. All right, so a pretty picture of sunset on obsidian. The Three Sisters and Broken Top. Broken Top is about 300,000 years ago, or 300,000 years old is the oldest rocks at Broken Top. The youngest rocks are about 150,000. So Broken Top itself kind of spans about 150,000 years, and it hasn't had an eruption for a very long time. But I do have to present in here because South Sister, on the south side of South Sister, there are lava flows. You can see them by Sparks Lake and Devil's Lake. And if you hike up into the Green Lakes area, you're on the edge of these lava flows that are 2,000 years old. So South Sister, again, is very young, definitely capable of erupting again. There's, you probably know, there's magma that has come in on the west side of South Sister, right around kind of the 1999, 2000. There was an uplifted area on the west side of South Sister. That's an influx of magma coming up beneath the volcano, and it has been sitting there ever since, just kind of causing an uplift because that magma is hot, so it heats the rock above it, warm things expand, and so the surface of the earth expands just a little bit, just by a few centimeters. It was about 1 inch per year that was kind of inflating, and that's just what we would expect at active volcanoes. That's not a clear sign that the volcano is going to erupt. That magma could just sit there and cool slowly and never erupt, but it is a clear sign that that's an active volcano, and we could expect future activity at South Sister. And really, this whole area is, all still volcanically active. All right, so that was convergent plate boundaries, subduction zones. We're going to leave subduction zones now and talk about volcanic activity that's caused by other processes, other tectonic processes. So we're going to move now to divergent plate boundaries, where two plates are moving away from each other. And most of the places on the planet where two plates are moving away from each other are underwater, like here in the Pacific Ocean. But they're not all underwater. There are places where we can see that happening on land, and where that pulling apart or moving away from each other is actually starting to separate continents. If you think of the East African Rift, that's a place where the African plate is being separated, it's being pulled apart by a new divergent plate boundary. If that activity continues, then the East African Rift eventually will drop down below sea level, and there'll be this sort of linear sea that kind of invades into East Africa. And then if it continues for millions of years, a whole ocean will open up between the very eastern part of Africa and the rest of the continent. So that's how oceans open and close. That's how all the plates used to be together in Pangea, all the continents used to be together in Pangea, and they've separated out. That has happened many times throughout Earth's history. So continents, was there a question? Yeah, the Red Sea is kind of like further along than the East African Rift. It already has filled up with water, yeah. All right, so continents can be rifted apart, and you can actually kind of see that here. This is drawn not quite, so that this image is sort of for our part of the world, but not like exactly. And this is showing a full divergent plate boundary. Like here's one plate here, and here's one plate here, and they're moving away from each other. That is not what's happening in North America yet. It could happen in the future. It will be millions of years into the future. So if you're waiting to see that, like, actual physical rift of the United States instead of just the political one, we're gonna have to wait for a long time for that to happen. So millions of years from now in the future, this could be what the future of North America looks like, but it isn't there yet. So we'll talk about just the early stages of that rifting. All right, so we'll go back to this map and notice here, this is a divergent plate boundary in the mid-Atlantic ridge. This is where the North American plate and the Eurasian plate are moving away from each other, or where the North American plate and the African plate are moving away from each other. There are divergent plate boundaries in the Pacific as well. And if you look at this divergent plate boundary, where plates are separating, it actually kind of like almost seems to disappear in the Baja area. And then it transitions to, that's not a divergent plate boundary, that's the San Andreas Fault. That's a transform plate boundary where the North American plate and the Pacific plate are rubbing against each other. And then it transitions to a subduction zone. So we're gonna take a lot of kind of closer looks at, like, we have the subduction zone here in the north, the transform plate boundary here in the south, and then we have this divergent plate boundary kind of disappearing underneath North America. So let's and then we can also look at that in another version. This, as I go to this next map, we're looking at plate boundaries here. In this map, we're looking at ocean bathymetry, so the depth of the ocean. And so where you see these sort of gray or black areas, those are mountain ranges underwater. So they're a little bit higher. The ocean isn't quite as deep there because there's an underwater mountain range there. And then where you see the dark blue, the ocean is very, very deep. So if I go back and forth between these two maps, there's the divergent plate boundary in the mid-Atlantic. And there it is. You can actually see the divergent plate boundary just in the topography of the sea floor. That underwater mountain chain is created by those plates moving away from each other and producing volcanoes where they're moving away from each other. And if we go back and we look at the Pacific, that divergent plate boundary there it is in the bathymetry. And you can really see that it kind of disappears right at the Baja area. And that not only, so this represents the Pacific plate and other plates, the South American plate, moving away from each other. And then it disappears here, but this, on the surface, this divergent plate boundary is under the continent, but on the surface of the continent, you can see that Baja is kind of separating away from North America. So we'll look at that in a little more detail in this animation. And I can kind of stop this and make it go a few times, or we can repeat it a few times. It's gonna happen pretty quickly, but we can watch it as many times as we need to. So when I start this animation, it's going to start at 40 million years ago, and it's going to progress to today. So we're watching 40 million years of history of subduction. And this is, so here's the Pacific plate. Everything to the left of this line is the Pacific plate. Everything to the right of that line is the Farallon plate. 40 million years ago, there wasn't anyone around to call that the Farallon plate. This is just something that geologists, the Farallon plate is gone. We're going to see where it goes in a minute, but geologists call it the Farallon plate, even though it doesn't exist anymore. So I'm going to start this animation, and we're going 40 million years ago, and that Farallon plate is subducting underneath North America, much like, I'm going to go back and start that again. So it's subducting underneath North America, much like the Juan de Fuca plate is subducting underneath North America today. And actually, if I let it keep subducting to about 35, 25 maybe million years ago, it is the Juan de Fuca plate. So let's go back and start that again. The Farallon plate is a much larger plate. If we let's go back a minute here. No, that's too far. Sorry. Here. There's the Juan de Fuca plate. It's subducting underneath North America. If we go back in time and pull that plate back out, we reverse time, we go 40 million years in the past, and we pull that subducting plate back out of the mantle, we're going to have a much larger plate. And there it is. So the Farallon plate is just what we used to call the Juan de Fuca plate if we were around 40 million years ago to call it something. All right, so everyone good with that? This is just the predecessor to the Juan de Fuca plate. It's subducting underneath North America, which means everywhere along the entire west coast of North America, from Baja all the way up to Canada, there's a subduction zone, and there's volcanoes like the Cascades. They aren't the Cascades. Well, it's the early stages of the Cascades here, but prior to that, there were Cascade-like volcanoes all throughout California. And we see the remnants of that now in the Sierra Nevada. If you think of all the granite in the Sierra Nevadas, that represents the magma chambers that were feeding volcanoes up on the surface. And those volcanoes have long since been eroded away, but we can see all of that beautiful light-colored granite rock that was the magma chambers beneath those volcanoes. All right, so until about 30 million years ago, there was subduction all along the west coast of North America, and at about 30 million years ago, that Farallon plate, that little corner of the Farallon plate, disappeared beneath North America, and now the Pacific plate and the North American plate are side by side. This is the birth of the San Andreas Fault. This is the little baby San Andreas Fault. It's just not very long at all, But as more, you can see, as more and more of the old Farallon plate disappears underneath North America, the San Andreas Fault is going to grow longer and longer because there's more of the Pacific plate and the North American plate that are now touching. So we're seeing the San Andreas Fault fully develop, and then we're also seeing the last little remnants of the Farallon plate here and here, which is why we have subduction zone volcanism in the Pacific Northwest and also in Mexico. But in between, we have this transform plate boundary. When this last little bit of the Farallon plate, which we now call the Juan de Fuca plate, when the Farallon plate and the Gorda plate disappear, there will be a transform plate boundary from Mexico to to Alaska, essentially. And the Cascade volcanoes will go extinct. All right, so I'm going to just play this one more time because also notice now, right there, a divergent plate boundary, the separation between the Pacific plate and the Farallon plate is going underneath North America. So this is where things get really crazy in terms of 3 dimensions. You have to think of, here's North America, here's the subducting Farallon plate. Maybe I should do it the other way for you guys. There's North America, there's the subducting Farallon plate. But the Farallon plate actually has a divergent plate boundary in it. So picture my hand right here where my knuckles are, picture that that's a divergent plate boundary. And this part is moving this way, and that part's moving that way. Okay, this is the Pacific plate, this is the Farallon plate, here's North America. This thing is moving relative to each other, these things are moving this way, away from each other, but they're both moving this direction at the same time. So there's multiple movements that are going on here. This whole thing's moving this direction, but this one's moving this direction a little faster, and that one's going that way. And then the whole thing subducts underneath North America, and now there's my knuckles. That's a divergent plate boundary underneath North America. Does everyone kind of picture that? There's a lot going on there. Yeah. No, but it sounds like something I should read.
San Andreas is obviously an issue, but by far you don't want to live in Carson City.
Because of earthquakes? Yeah, yeah.
Layman can easily read this book.
Yeah. So rough-hewn land. Yeah. So book recommendation. Probably the library has it. Or we'll get it for you. All right, so right here we're seeing that divergent plate boundary disappear beneath North America, and now it is more and more of it is underneath North America, kind of south of the Nevada area. But now watch what happens to North America as that divergent plate boundary underneath North America continues to pull apart. It pulls, it like stretches the surface. The continent, the North American continent, is getting stretched. And so I'll play that one more time, and this time just look at these little states are all smushed up. There were no state lines 20 million years ago, but if there had been, we would have been able to watch over time as those states got bigger and bigger and bigger because that western part of North America is being pulled apart. And it might be because of this divergent plate boundary underneath North America. This is just one. So what is going on to cause stretching or pulling apart of the Great Basin? This is essentially what we call the Great Basin, or areas that are dominated by basin and range geology. So most of Western North America and into Southeastern Oregon. There's a lot of, we don't fully understand all of the geology for why this is being pulled apart. So I've just presented one hypothesis for why that is. Perhaps it is this divergent plate boundary that has disappeared beneath the continent. Yeah?
It's more like Baja California is moving northwest.
Yeah. So parts of California are moving northwest, and we're going to talk about that, I think, in the next few slides, maybe in the next slide. I don't remember for sure. So yeah, that's a good comment, and we'll get there. All right, so this kind of sums up what we've talked about so far. There's the Juan de Fuca plate subducting here, but there's a northwest movement here along the San Andreas Fault where the Pacific plate is moving northwest, and then there's pulling apart in Western North America in what we call the Great Basin. And that does include southeastern Oregon. All right, so that pulling apart, that kind of what could be a new divergent plate boundary if it continues, that causes extension, And the way that the crust of the Earth responds to extension or pulling apart is to fault. These fault blocks are formed. So this all was continuous, just one layer, and pulling apart or extension, these forces here on that land. That rock is brittle, and when it's like pulled apart, it breaks, and it breaks in fault blocks. So this is a fault right here. This is another fault right here. This is another fault right here. So this is a block that dropped down lower relative to its neighbor. And that creates what we call basins in between the faults and ranges. So that whole western part of North America that we call the Great Basin, it's called that because it's defined by basins and ranges. And those basins are the result, the basins and the mountain ranges are the result of faulting, blocks that have dropped down relative to their neighbors. So this type of topography, kind of like a really steep fault face or fault scarp on one side, and then a really gradual topography on the other side, that's really indicative of what you see in this type of geologic setting. And we're going to see that in some of the images that we look at for Oregon. So extensional forces result in faulting of the Earth's crust and also in volcanic activity. So this is kind of a weird image because it shows the crust of the Earth and then it just shows this white area like there's nothing else down there. But that's the mantle down there. And remember I said the mantle is solid. It's not molten. It only melts in a few places. One place is where hydrogen and oxygen has been introduced into the mantle. That causes it to melt because it lowers the melting temperature. But another place where the mantle can melt is where the pressure on the mantle is lower. Here, the crust of the Earth is very thick and the pressure on the mantle is high, so it can't melt. It's hot enough to melt, but it can't melt because the pressure is too great. Here, the crust of the Earth is thick. The pressure on the mantle is too high, it can't melt. Here, the crust of the Earth has been pulled apart. It's thinner than it is in those other two places, and that means the pressure here is lower. And just by lowering the pressure, the mantle is able to melt, and that generates magma, and that rises up and feeds volcanoes. So in divergent plate boundaries on continents, early phases of divergent plate boundaries, where the continent hasn't been pulled apart yet, but it could be over time, we would expect to see volcanic activity. And that's exactly what we see in the Great Basin of Western North America. And we also see it in the East African Rift. There are volcanoes in the East African Rift, even though there's no subduction zone. That's because the crust of the Earth has been thinned, pulled apart. The pressure on the mantle is lower in that region, and that allows the mantle to melt and rise up and feed volcanoes. All right, so these faults extend. So if we think of these faults that are causing basins and ranges, those extend into Oregon. So here are these faults that represent, that's a mountain range, and below that is a basin. This is the Steens area and the Alvord Desert. And then there's the Hart Mountain is another fault block, and there's a basin here, the Werner Valley. And then Abert Rim is a fault block, and Lake Abert is a valley. And then Winter Rim and Summer Lake is a valley. So we have these basin and range fault blocks throughout Oregon as well. And then we also have all these faults that run kind of northwest that are different from basin and range fault, but related to them. So smaller faults, but much more of them. And notice those run right through, underneath Newberry, through Bend, and into the Cascades. And then we kind of get almost basin and range faulting in the Cascades. It starts to run north-south again. That's Green Ridge. And it also is a fault block, very steep. The western slope of Green Ridge is very steep, and the eastern slope is very gradual. All right, so let's look at some images of that, starting in southeastern Oregon, kind of moving across the state. So the Pueblo Mountains in southeast Oregon, we don't quite get the scope of the faults here because of just how this image is taken, but these are all fault blocks. They're all mountains because another block has been dropped down relative to the higher topography of the Pueblo Mountains. Here you can see it much more easily. This is Mickey Basin, which is, the Steens is right there in the background in the clouds. You can see some snow. So that's Steens Mountain. And this is really typical of fault blocks. Gradual topography on one side and a steep face on the other. Gradual topography here, steep face. Here's the steep face and gradual topography behind it. There's another steep face and gradual topography behind it. There's another steep face and gradual topography behind it. Everything we're seeing in here is a fault block. So this is very typical of southeastern Oregon and very typical of any kind of area that's getting, where the continent is getting pulled apart. You see this type of activity or this type of topography in Iceland. You see this type of topography in the East African Rift. Those are all places where things are getting pulled apart. Steens Mountain is a big fault block. This is not getting pulled apart here. This is the whole Steens Mountain area is higher relative to the Alvord Desert, and it was high enough that it was glaciated in the past, and this is actually a nice glacial valley. That's not being pulled apart. That was just carved out by ice, but it's very spectacular. There's a great view of a fault block, Abert Rim, so very steep on the west face, and the east face is just very gradual off to the other side. And then this is the basin that corresponds to it. And then this map just shows a bunch of those areas as lakes. So let's see, we looked at Alvord, so Steens are here, and this would be the Alvord Desert. But during the last glacial maximum, so like 14,000 years ago, that was full of water. There was more rain, more snow, and so those basins filled up with lakes. And so you can kind of see the basins just by, we don't even need, this map doesn't show topography. We can't see the mountain ranges, we can't see the faults, but we can tell that there's this whole linear sort of assembly of basins across southeastern Oregon because they filled up with water during the last, so kind of 35,000 years ago to 12,000 years ago, these Pleistocene lakes. And Alvord Lake now is gone. Sometimes there's a little bit of water in the desert. Catlow Lake is pretty much gone. Here, Harney Lake, the blue, the dark blue is the extent of what it is now in a good year. And let's see, Warner Lakes, there's a series of little lakes in the Warner Valley, those little blue dots that still exist. Goose Lake on the Oregon-California border. So all these lakes, some of them still exist, some of them are completely gone and are just dry lake basins. Yeah, so Fort Rock is here. It was a very huge lake called Fort Rock Lake, and now there isn't anything left of that lake. So this is what those areas look like now. This is the Alvord Desert. This was a lake. As it evaporated, it left behind salts and alkali flats. So that's what we see in these basins now. Just another great photo of Alvord Desert. All right, so we have been talking about plate tectonics kind of on a large scale, and the big picture is these plates move around as coherent blocks, individual blocks moving around, and that's kind of the simple version of plate tectonics, that here the Pacific plate is moving northwest and the North American plate is moving southwest, and that's it. That's like as deep as we need to go, but that isn't necessarily the case for plate tectonics. It can be more complicated than that, and some plates can consist of individual blocks that move at different speeds in different directions. If I back up just a minute, North America, the actual original edge of North America is over here, kind of in the Oregon-Idaho border. Everything west of Idaho has been added on in the last 200 million years or so. So it isn't part of the original North American continent. It's stuff that has been added on over time, and that's sort of the topic of a whole nother talk. But it means that the edge of North America isn't going to move as one coherent unit. It's going to be affected by these plate movements, and it's going to do some squirrely things. So we're going to look at that in this animation. So this is showing the Pacific plate and the San Andreas fault. It's going to start at 20 million years ago. That's right around when the San Andreas fault, remember in that last image, sort of the birth of the San Andreas fault. It's been around for a little while when this image starts, a few million years. So the Pacific plate is going to be moving this way, and the Juan de Fuca plate is going to be moving this way. There isn't an arrow for the North American plate, but it is also moving. And so this transform plate boundary, where the Pacific plate and the North American plate are scraping past each other, what we'll see is that movement of the Pacific plate actually drags along some of the western part of the North American plate with it. So we're seeing the San Andreas fault develop, but we're also seeing blocks of the North American plate get scraped and dragged along with the Pacific plate as it moves. So I'll start that again. Let's go back. And you can watch that again. So coherent blocks of rock will move as one unit, but they'll move separately from other coherent blocks of rock. So if people are familiar with like the transverse range in California, it's this mountain range that is running east-west when most mountain ranges run north-south. It has been dragged into that position by the movement of the San Andreas Fault and the Pacific Plate, dragging it to the northwest. So there was a comment earlier about California, parts of California are moving to the northwest, and this is the reason for that. So this impacts Oregon, another animation that we'll look at multiple times. This impacts Oregon significantly, hugely. So here we have the Pacific Plate. We're going to start big with big scale plate tectonics. The Pacific Plate is moving northwest. The Juan de Fuca Plate is moving east, maybe kind of northeast a little bit. And Basin and Range here has this extension or spreading that has kind of a force that's going towards the northwest. So don't pay attention to anything else on the map except those yellow arrows, those 3 yellow arrows, and just kind of watch as this goes, that movement, and that movement. We have these 3 major movements that are affecting the Pacific Northwest, and Oregon and Washington in particular. And those 3 movements are driven by the movement of the Pacific Plate, the movement of the Juan de Fuca Plate, and the extension of the Great Basin. So just pay attention to those 3 for now, and then we'll break this down individually, and we'll start down here with the movement of the Pacific Plate. As it moves northwest, it's pulling the Sierra Nevada block, which is purple, along with it. And the reason it's pulling the Sierra Nevada block along with it is that is all granite. It's a big, huge, coherent block of granite. And if it feels a pull by the Pacific Plate to the northwest, it will move as a unit. It won't break up into pieces because it's just like solid granite. So the whole the whole Sierra Nevada block is being shoved into Oregon, Western Oregon, by that movement of the Pacific Plate. So there we can see the purple being shoved up into this pink block of Western Oregon. And I'll start this again in a minute, but first I want to talk about that pink block. It is also a solid, coherent unit of rock. It is all basalt. It's this terrain or kind of piece of geology that's called Silesia. And it's basalt that was erupted underwater, offshore of Oregon, and then smashed onto the edge of the North American continent. Remember I said a lot of this stuff from like the Oregon. Here's the original boundary of the North American plate. All that tan stuff out there, that's North America, and everything else has just been added onto it. And Silesia is just part of what's been added on to the edge of North America. So underlying the Willamette Valley and the Puget Sound area is this solid, cohesive unit of basalt. So when I start this over again, and the Pacific Plate drags the Sierra Nevada block up to the north, the Sierra Nevada block pushes on another solid block of basalt, and it isn't going to break up or do anything squirrely either. It's just going to move to the north as well. So we have these 2 blocks shoving up into this green block in the Seattle area. And the green block isn't as solid and coherent. It just isn't a solid piece of rock. It's made up of a bunch of stuff, mostly the North Cascades that are all different types of rock. So it doesn't behave as one unit. And it's also kind of pinched between this fixed part of North America that isn't going anywhere. It's moving. North America is moving along with the rest of the continent, but this rock is moving as one solid cohesive unit. And so this little thing finds itself sort of pinched between movement from the south and no movement at all. And so it gets squished or shortened, and a bunch of faults appear running east-west through this area. And that's why there are east-west trending faults in the Seattle area, and why there are earthquakes like the Nisqually earthquake along those faults. Okay, so we've accounted for what's going on here. Now we're going to look at what's going on here. So if I start this again, we not only have this movement from the south because of the San Andreas, but we also have this force that's kind of moving things to the northwest because of Basin and Range, or a divergent plate boundary, or an early divergent plate boundary. And we have a movement to the east or to the northeast because of subduction of the Juan de Fuca Plate. So if we kind of tally up all of these forces, we get rotation of Oregon and Washington, which is what these yellow lines are showing. This is showing no rotation here. It's just moving north or northwest. This is moving northwest. And then we start to actually get some rotation that is hinged around this area along the Columbia Gorge between Oregon and Washington. So this whole part of the Pacific Northwest is rotating clockwise because of this force, and this force. And now we'll watch one more thing on this, and that is what happens here to this blue area and here to this orange area. This dashed blue line represents where this blue area started, and this dashed orange line represents where the orange area, which is the Cascades, started. So I'll start that again. There they are in their original positions, and this clockwise rotation occurs and rotates these, the blue and the orange area, clockwise. And what that causes in the blue area is more pinching or shortening, because it's sort of getting pinched between movement, pushing it to the northwest, and then this area being solid, not going anywhere. And that also creates east-west trending faults, and that's the Yakima fold belt. So if you ever travel north on Highway 97 and you go through the Yakima area to Ellensburg and you're going up and down these crazy hills, the freeway, like it's a 4-lane freeway at that point, it's going up and down, up and down. You're going up and over folds that are these faults because of that part of the state getting pinched. And then the Cascades started east of where they are, and they rotated to the west because of this rotation of Oregon, and then newer, younger volcanoes sort of appeared to the east. And that's also the subject of a whole nother talk. That's kind of in the last 50 million years.
What happens to the Columbia River during cloud?
It just keeps carving its way through, like the water just keeps, as things are moving, like as rocks are kind of coming up around it, it just keeps its path. So it's sort of keeping pace with all of this, cutting, eroding as all of this happens around it. All right, so here's the actual data. So I didn't just make that up, even though it sounds like it. There's data that supports this. And there's other ways that we can see this rotation. We can see it recorded in the geologic record, but we can also see it through GPS data. So everywhere where you see a blue arrow, so first of all, if you see an arrow this long, that represents 10 millimeters per year of movement. Again, that's something we can kind of wrap our minds around. Some of those arrows are much longer, up to like 20 or more millimeters per year of movement. If it's a blue arrow, that's a GPS survey. So that's people going out and collecting GPS data with very precise GPS instruments, not just their phones. And then if it's a red arrow, that's a permanent GPS station that is set up always collecting data. And so you can see that this rotation is centered somewhere here. There's no rotation there. That's the hinge that everything's rotating clockwise around. There's less rotation here and more rotation along the coast, and especially as you go up into northwestern Oregon and Washington. And this rotation, this clockwise rotation of the Pacific Northwest, has done what plate tectonics did for geology in the 60s and 70s and just sort of reformatting our understanding of the planet. This has done the same for the geology of the Pacific Northwest. We have so much better understanding of things that were a little bit mysterious prior to when we realized that Oregon and Washington are rotating. There was maybe a question. You mean in terms of time? Yeah. Yeah, so that blue line, that just represents that, so like here, if we go to like this red line, this thing is always collecting data, continuously collecting data. And so that means that last year, this isn't last year's data, but whatever year this was collected in, let's say it was, 2015, that's where this was in 2015, and in 2016, that same GPS unit was now there. It had moved that distance. Does that answer your question? Yep. Yeah, and this is happening every year. So this amount of movement is happening every year. We're looking at older data from a few years ago, but if we looked at this year's data, we would see something very similar. Yeah.
A lot of activity, why aren't there more earthquakes?
Yeah, so why? So the question is, there's a lot of movement. Why are there more earthquakes? And there are. I don't have an image in this talk, but there are faults. Actually, we saw that image. How far back do I have to go? There's all those faults that run through Oregon, and we could have earthquakes along these faults. They're as far as we know, they're active, and we haven't historically had large earthquakes. There have been here in Klamath Falls, and out here. Not as large. There are smaller earthquakes. So we could expect earthquakes. And we do feel, this doesn't show the faults on the west side, but the Scotts Mills earthquake, when was that? Yeah, but the Klamath Falls ones were maybe 93. Scotts Mills, I feel like, was more recent. But there have been earthquakes in the Willamette Valley, in the Portland area, in the Seattle area. And so even though on a human timescale it seems like we don't have a lot of earthquakes in this part of the world, on a geologic timescale we do. It's a great question. No, that's just a rotation. That's just where this rotation is occurring around. But it's not a hot spot. But we are going to move to hot spots now because I have to wrap this up really quickly. It goes to 11:30 with questions. Is that right? Okay. All right. So we're okay. All right. So hotspots. Remember, hotspots are not a plate boundary, but they are large tectonic features. And in this image, there's a hotspot shown here. This is a plume of hot material that comes up from perhaps deep in the mantle. We don't know a lot about hotspots. There are a lot of people who spend their entire careers trying to answer questions about hotspots. They might come from deep in the mantle. They might come from more shallow parts of the mantle. What we know is that they do at some point get up into the crust, and that hot material causes melting, and that feeds volcanoes. So this is drawn to represent Hawaii. Hotspots are stationary, and the plate moves over the top. So in this next image, we can see there's that hot material rising up through the mantle. It's drawn in yellows and reds and oranges, so it makes you think this is all molten, but none of it is molten. This is all solid. This is solid mantle, and this is solid, hotter. This is solid, very hot mantle, and this is solid, even hotter mantle material rising up through the mantle. So it's crazy to think about solid materials moving, but that's how you have to think of the interior of the planet. They move, they can bend, they can deform, they behave as a plastic material, not plastic like what people make, but that they can bend, but they're not molten. This isn't molten material. So solid hot material is rising up. When it gets to, this is representing time, so it takes, I don't know, millions of years to come up. When it gets to the base of the crust, it causes melting, partly because high temperature material came up relatively quickly. So this is hot, but this is even hotter. So it melts some of this upper part of the mantle. Another reason that melting occurs is that this is under immense pressure. It's not going to melt. It's hot enough to melt, but the pressure is way too high. Once it gets, so down here, pressure is very high. It can't melt, it can't melt, it can't melt. Once it gets up here, the pressure is lower, and so it actually can melt for two reasons. One, there's heat that's added to the upper part of the mantle, and two, this material feels lower pressure than it did down here. So that causes a lot of melting material of the mantle. That rises up and feeds this just outpouring of flood basalts. So think of like what we see in Hawaii, volcanic activity in Hawaii, rivers of lava covering the landscape, but way more than is occurring in Hawaii. Just huge amounts of, miles and miles of basalt, molten basalt rock that eventually solidifies and forms what we call a flood basalt province, because it erupts so much material that it actually represents a huge geographic area. We'll look at an example in a minute. But the plate is moving through this whole thing. So the plate is moving off to the left, the hot spot is stationary, the plate is moving off to the left, which means the flood basalt province gets dragged off the area where the magma is being produced, and a volcano forms in that area. And that plate will keep moving to the left, and these volcanoes will get dragged away from the area where magma is produced, and a new volcano will come up. And so you get a chain of volcanoes that is age progressive. The oldest ones are farther away from the hot spot, and the youngest ones are right over the hot spot. So that's very different from the Cascades. The Cascades is not age progressive. It's because there's subduction, and that's creating a range of volcanoes, but those volcanoes can all erupt theoretically, they could all erupt at the same time. They don't, thank goodness, but there's no age progression in the Cascades. And a hotspot chain, there's always age progression. Yeah, so the Hawaiian Islands, the older Hawaiian Islands are off of the hotspot, and we wouldn't expect to see volcanic activity there. We would only expect to see volcanic activity in the ones right over the hotspot, which is the big island of Hawaii. Yeah, so Yellowstone is where we'll go next. So this image is this is drawn for Hawaii, and that's an oceanic plate, that's the Pacific plate, but this could be the North American plate, and there is a hotspot underneath the North American plate, and that's the Yellowstone hotspot. So we're gonna go back 17 million years ago. Here's Oregon and the border with California and Nevada and the Idaho border, and then here's Washington here and Idaho. All right, so hopefully that sort of orients you on the map. And about 17 million years ago, these lines represent kind of cracks or fissures that opened up, and huge outpourings of basalt occurred. And so this is like rivers of lava, like what we see occurring in Hawaii, but on a much larger scale than what is happening in Hawaii today. So for millions of years, basalt covered most of eastern Washington and most of eastern Oregon and all the way through the Columbia and out to the Pacific Ocean in some places miles of basalt. So this is the Columbia River basalts. The Steens basalts are part of it. It's all the same. It's all related to the same thing. We just have it separated out into two different names, but it's all the same, the result of this hotspot that was underneath probably this part of Oregon at the time and erupted huge amounts of basalt. And then the North American plate, so that hotspot is there underneath southeastern Oregon, but the North American plate is moving to the southwest and the hotspot is stationary, which means that there should be volcanic activity right above the hotspot at 16 million years ago. But then as the plate continues to move southwest towards me, but the hotspot is stationary, by about 12 million years ago, that volcanic activity is now in what we call the Snake River Plain of Idaho, because the plate is moving. This looks like volcanic activity is moving, but the plate is moving over the top. And now that activity is located underneath Yellowstone. And so the most recent activity of the Yellowstone hotspot, in terms of large eruptions, was about 500,000 years ago, 600,000 years ago, and one of those huge eruptions of the Yellowstone hotspot that formed the Yellowstone caldera. All right, so we can see the Steens basalt and the Columbia River basalts exposed very nicely in Oregon. So we're looking now, we know we're looking at fault blocks because we see these steep faces on one side and gradual faces on the other in the Steens Mountain. But now we know that the rock that makes up all the layers exposed in these faults is all Columbia River basalts. In this case, Steens basalts, but it all erupted at the same time. It's all part of the Columbia River basalts. And here you can kind of see those lines in the Steens Mountain. Those are all individual lava flows of those Columbia River basalts. Here we're at the top of Abert Rim looking down at Lake Abert, and this is a piece of that basalt, but this whole rim below us is all lava flows from the Columbia River basalts. Sutton Mountain, again, that's in the Painted Hills area. You can see those lava flows of the Columbia. This is all basalt, all erupted as part of the Columbia River basalts. Another picture from Sutton Mountain in the John Day. You really, I think I have a bunch of pictures of the John Day because it's just gorgeous, layer upon layer upon layer upon layer of basalt. All right, I have fewer pictures of the John Day than I thought. That's all right, so not only did this hotspot activity produce basalt lava flows, it also produced these huge kind of caldera-forming eruptions, and they tend to form a rock called rhyolite, and we can see those exposed in southeastern Oregon. So we would expect to see them here, right? Because that's where all those big calderas are in Oregon. And sure enough, if you go to the Oahe area, there's just fantastic exposures of rhyolite. This is near Iron Point on the Oahe River. This is at river level looking up at these spectacular cliffs. And this is in the same place up above at Iron Point looking down at the Oahe River. And this is all rhyolite erupted from those huge eruptions 16 million years ago, 15 million years ago. The Oahe Canyonlands just expose fantastic examples of rhyolite. from these. All of this is rhyolite from those eruptions.
Can you explain the column or the salt?
Yeah, just really quickly, and even rhyolite can do it a little bit. You can kind of see some columns here. So that material is deposited, it's warm, you know, when it is produced, and it cools. And as it cools, it contracts. And the columns are just a result of cooling. They're fractures that form as it cools. And if it cools really uniformly, really like evenly, then the columns will be almost perfect hexagons. And if it cools, you know, just like it's losing heat in different areas, at different rates, then it won't form nice columns.
So is that what happened at Warm Springs?
Yeah, yeah. So anywhere you see nice basalt columns, that just means that it cooled slowly and evenly, and it contracted and formed those hexagons. Okay, so this is all pretty clearly related to the Yellowstone hotspot, but there are some other calderas here in Central Oregon. And the Crooked River caldera in the Prineville area is about 30 million years old. And there's some speculation that perhaps that is an earlier version of the Yellowstone hotspot. And then there's also this Siletzia. Remember Siletzia? Like before it rammed into Oregon and made up the bedrock of the Willamette Valley in the Puget Sound area, it was volcanoes, it was basalt erupting offshore underwater off the coast of Oregon. And there's some speculation that perhaps that was related to the Yellowstone hotspot. So the Yellowstone hotspot might be much longer lived than just the last 17 million years ago. It might be actually have been shaping the geology of Oregon and the Pacific Northwest for much longer than that. The Crooked River caldera, so this is just all these spheres represent different volcanic eruptions. So this is Mount Mazama, 7,600 years ago. This just represents the volume of ash that was erupted. So it's sort of kind of gives you an idea of how large that eruption was. This is Mount St. Helens, 1980 eruption of Mount St. Helens. This is Pinatubo, 1991. And these are all big caldera eruptions of Yellowstone. This is Yellowstone. This is actually Long Valley caldera in California. Yellowstone, and that's Toba in Indonesia. All that I'm just showing, the only reason I'm showing this is that there are these huge eruptions, highly explosive eruptions that have occurred throughout Earth's history. And the Crooked River caldera is on that scale of like what Yellowstone and some of these other huge eruptions have produced. So perhaps that's related to the Yellowstone hotspot, perhaps not. That is a topic of ongoing research. But here's the result. Smith Rock and all that rhyolite in the Prineville area is all a result of the Crooked River caldera, perhaps related to the Yellowstone hotspot. Okay, so we've gone through these tectonic forces, kind of big picture, and then narrowing that down of subduction, continental extension, and hotspots, and that these have created the landscapes we see throughout Oregon, and particularly throughout southeastern Oregon. And these geologic processes are constant, and they continue today. None of this has stopped. We're still moving, we're still rotating, and North America is still moving as a whole cohesive unit. And so this is all still shaping Oregon. We could still see earthquakes, we could still see volcanic activity. And this talk has really tried to highlight some of the sort of newer research that helps explain our understanding of these processes. So that's it for that talk. Went a little longer than I expected. I apologize for that, but I'm happy to answer more questions. Yeah. Oh. Yeah, there's a question in the back.
The periods that you illustrated in terms of millions of years, is that a characteristic period that things took place and then they essentially have a greater period of where they'll happen again? Or is it random between those periods that takes place?
Do you mean when I was showing some of the photos of like the Clarno Formation or the John Day Formation, I had a time bracket on it? Is that what you're?
Most of the explosions, if you will, seem to be millions of years ago.
Like heat, more like this?
Right.
Yeah, okay. So that's a good question. So the Columbia River basalts and the Steens basalts, that was over a period, that started about 17 million years ago. And most of this was erupted by 16 million years ago. So it lasted over millions of years. Each one of these calderas, that was one highly explosive, catastrophic event that maybe lasted a few days or maybe a few weeks. So we have both. I think if I'm understanding your question right, are these lasting, like, are they individual events, or do they last a long time? This lasted a long time, and it was erupted over millions of years. On a human time scale, that's a long time. Geologically, for that amount of basalt to come out over a period of a couple million years, that's still pretty crazy. But it did last for a few million years. Each individual caldera is one just life-ruining event. Does that answer your question?
To a part. So can you actually think of in terms of where any of this is going to take place again on a forecasting basis because of what's taking place?
Yeah. Yeah, so these processes are still happening. There's no indication that more, so large eruptions of basalt occur when that plume head kind of initially impacts the base of the crust and generates a lot of melt. And there's no indication that that could happen again in this part of the world, that this isn't going to repeat itself. But these have been happening sort of punctuated throughout time for the past 16 million years, and the last one was only 500,000 years ago, which is only 500,000 years. It's like a lot for us, but geologically not. So that, and we can image that there's still magma and there's still a hotspot beneath Yellowstone. So it's very likely that there will be another huge life-changing, and I mean globally life-changing eruption at Yellowstone sometime in the future. Can we predict when that will be? No. Absolutely not. Like, they don't follow. We can average out how often these have all occurred over the last 16 million years. And then you get these things like Yellowstone is overdue for an eruption, and volcanoes are never overdue. Earthquakes are never overdue. They don't follow averages. So yes, something is very likely to occur here in the future, but we don't know when. Does that help?
Yeah.
All right, over here, I'll kind of work my way around this way. So in the back.
I wanted to go to the subduction zone earthquake and then the volcanic activity that might happen, because we keep saying this subduction zone earthquake is imminent, whenever.
But not overdue. Yeah. Yeah, so that question gets asked a lot. And the, how far back do I have to go? I don't know how worthwhile it is to do this kind of thing. But now that I'm doing it. Okay, so the same process generates volcanoes and earthquakes. Here, the plates are locked. That generates earthquakes. Here, they're not, and that's generating magma. That magma is rising up and feeding volcanoes. So if this stress is really, the locking that's occurring there that's building up stress, when that is released, that is a huge earthquake. That kind of releases the stress here, but it doesn't really impact what was happening down here. This was moving all along down there. So magma is being produced the whole time. It's rising up and it's feeding volcanoes. And so there's no really direct relation between what happens here and this magma production. So the good news is we can kind of, like if we feel the shaking of the Cascadia subduction zone, we're going to be in for some, some stuff for a while. But we don't have to just look out at the Cascades and wonder if they're all going to pop off also, because there isn't a direct relation between this and this magma production. However, it does seem the more people study volcanoes in subduction zones after big earthquakes occur, like in Japan and New Zealand and in other South America, other places where there are subduction zones, there could be magma shallow, like maybe at South Sister. We know there's magma that's shallow in the crust, it's sitting there, and maybe it will erupt in 50 years. But so it's kind of primed to, at some point in the future, erupt. But the shaking, not the actual big scale plate movements, but the shaking caused by the earthquake could maybe cause that magma to erupt in the next 5 years instead of the next 50 years. These are all just like, there's no data behind these numbers. This is just sort of a general example. So there is some evidence worldwide that perhaps volcanoes that were likely to erupt at some point in the future might erupt a little sooner because of a big earthquake. But again, it isn't like the earthquake happens and 5 minutes later the volcanoes are going off. It's just we need to be prepared for volcanic activity in our future anyway, and it might be a little sooner if there's a Cascadia earthquake in there somewhere. Is that all right? So there's a question here.
Yeah, so the layering of basalt layers that we see around here along our creeks and rivers, like Deschutes Canyon, Deschutes River, Metolius and all that, those are not, according to your map, they're not Columbia.
Right. Most of those are Newberry. Newberry is the largest volcano in the entire Cascade Range. It is not the highest, but by volume, it's the largest. And it's responsible in this image, now that I'm all the way up here, I can just keep going back to the beginning of the top. It's responsible for a lot of this red stuff that you see here. And so lava flows from Newberry they've been channeled into the rivers, and then we see them cut in those canyons.
And over what period of time have those?
Oh, the last kind of 400,000 years. So the ones in the bend area, the lava flows in the bend area from Newberry are about 70,000 years, 75,000 years. Yeah, like Lava Butte, the Lava Butte lava flow is from Newberry, and that's 7,000 years. So yeah, just on and off. And then there's also basalt lava flows, other volcanoes in the Cascades, or just other volcanoes in, maybe not in the Three Sisters region itself, but just here in Central Oregon. Like there's a lot of unmarked volcanoes on this map that could produce those lava flows. Tethro Buttes in Redmond is a really good example. They produce basalt lava flows. All right, so there's a question over here.
So the point, that sort of pivot point on the Washington-Oregon border, is there something observable, physical that you could see in that region?
Yeah, we should erect like a big
Yeah, right.
obelisk or something that. No,
But
and in
again,
fact, not only is there not something observable, but there's some debate among, so this is all within the realm of geophysicists. This is what geophysicists do, is like calculate all these stresses. And there's some debate among geophysicists of exactly where it is. They all agree that it's somewhere on that Oregon-Washington border along the Columbia River, but there's some debate about exactly where it is. So in the back, there was a question, and then I'll come back up to the front.
Yeah, when the subduction zone takes place, earthquake, how do you think it will affect us on the side of the mountain?
Yeah, so good question. So when that big Cascadia earthquake occurs, it could, so it has, in the past, we have really great evidence that it has ruptured or slipped or however you want to say, like the stress is building up here. And when that stress is released, that's rock breaking and that's an earthquake. So in the past, just the southern section has ruptured more often, and that usually generates a magnitude 8 earthquake. And sometimes in the past, the whole fault zone has ruptured or slipped, and that generates a magnitude 9. The last time that happened was in 1700, the year 1700, and that was the whole thing. So that was a magnitude 9. Either way, whether it's magnitude 8 or magnitude 9, we will feel shaking here. We will definitely feel shaking. And how many people have been in an earthquake? Oh, almost got me. I've never been in an earthquake. Well, I don't think maybe in that, but it's an A earthquake. So how long did shaking last?
Forever.
Yeah, how long for real did shaking last? 30 seconds, not that long, so sort of seconds. And then how long did it feel like it lasted? Forever. Big subduction zone, so a lot of those perhaps were California earthquakes. California earthquakes are usually in the magnitude 6, maybe 7, and they can last for seconds to maybe a minute, and it feels like forever. But a magnitude 8, magnitude 9 subduction zone earthquake is very different. They can last for 4 to 5 minutes, and that for real is going to feel like forever. And we will feel that shaking, so we'll definitely feel the shaking here. We will not feel it as strongly, obviously, as along the coast or in the Willamette Valley, but we will feel it. And there have been inventories of, buildings all across the state and how likely they are to collapse or be damaged. They don't have to fully collapse to be like unfunctional after an earthquake, especially because there would be aftershocks. So there have been inventories of public buildings like schools and emergency response buildings, the police and fire buildings. And there are a lot of buildings, obviously, on the coast of the Willamette Valley that are expected to collapse or to be unfunctional. But if you look at a map of those buildings throughout the state, I don't have it in this talk. It just shows these little red dots or orange, yellow dots or green dots for buildings. And if it's red, that means that it's, it's likely to collapse. And if it's blue or green, it's unlikely to collapse. So it's sort of using the scale. And of course, there's a lot of red dots clustered in the Willamette Valley and along the coast, but they're all through the state. The problem is we didn't have seismic codes in Oregon until like the 80s or 90s. And most of our, schools and police and fire buildings were built before that. And those seismic codes are for California earthquakes. California is a leader in engineering for earthquakes with good reason. They have earthquakes a lot. But those earthquakes are smaller and will last not as long as a subduction zone earthquake. And so not only do we need, an upgrade in our seismic codes, but we also kind of need to think about subduction zone earthquakes instead of just California type earthquakes. So we will feel the shaking here in Oregon, and there will be damage to buildings. Generally, if things were built before the 80s, they didn't have seismic codes. You should probably, if you live in one of those buildings or you spend a lot of time in one of those buildings, you should probably have an inspection to see what can be done to that building to get it up to code. And generally, if it was built after the 80s, it's generally going to be structurally sound. There will be, cracks in sheetrock and broken glass everywhere, but the building itself probably will be okay. So that's also the topic of a whole nother talk, is how will it impact us here? But maybe that's just kind of a general, another just quick thing I'll add to that is this doesn't have to be a scary event. We have the technology to withstand large earthquakes. We can absolutely be prepared for this, both engineering wise in our infrastructure and as individuals. Magnitude 9 earthquakes happen in Japan. Not all the time, but which way am I going? Got lost. This tsunami was devastating. It was larger than they expected, but the earthquake was a magnitude 9 earthquake, and you don't hear about much damage caused by the earthquake because there wasn't much damage caused by the earthquake. The tsunami was a surprise. It did take them off guard. But the earthquake, they were pretty much backed up and functioning after the earthquake with very little damage because their infrastructure was engineered for it. And we could do that here. And we as individuals, if we're just prepared with supplies on hand for a few weeks of being kind of on our own, this doesn't have to be a bad event. Okay, so question in the front.
Actually, what happened there is that they had built the wall for the tsunamis, but the land dropped
Yes.
7 meters.
Absolutely, and we are expecting the same thing here. So they learned a lot, multiple lessons in this, and that is so Japan is the most prepared nation on earth for earthquakes and tsunamis. And this is a seawall. That looks like a tsunami wave, but that's actually a seawall protecting this town. The water's coming over the seawall, and they have seawalls everywhere along the coast to protect these towns. And they built the seawalls high enough to withstand what they expected to be the highest tsunami that they would get. And so when this earthquake happened, that seawall would absolutely have protected them. But because of the earthquake, the land subsided by 3 feet, which means the seawall was 3 feet lower, and it could not protect them from the tsunami wave. So they and we learned a lot of things during that, which is you can expect subsidence. I have images in another talk for earthquakes that show we could expect in some places along the coast up to 6 feet, 3 to 6 feet of subsidence. We don't have seawalls. We don't have structures. They all had structures, kind of evacuation structures that they could go up and get out of the way of the tsunami waves. That saved thousands and thousands of lives in Japan. We don't have those. And then the other thing that Japan really kind of relearned in this event is up here in the hills. I don't know about this location, but in some places in Japan, there were ancient markers, ancient stone, 1,000-year-old rocks that said, do not build below this line because this is where the tsunami came. And they did build below the line, and they kind of relearned their own lesson in we can have much larger tsunamis than we expect if we just look back at our own records. Also, this is tragic for many, many different reasons, but another reason was there was current research. It wasn't just those ancient stone markers, but there were current geologic studies that were in the process of kind of just before being published that did document that there were larger tsunamis that had occurred in Japan. If this event had occurred 5-10 years after it did, Japan would have would have built up its seawalls higher because these new studies were coming out saying they can get bigger tsunamis than they expected. And they would have reacted to that. Japan wouldn't ignore that. They would take that literally. They would build. In fact, some mayors in some towns, there are stories you can kind of look through, do some searches, and there are individual mayors in towns along the coast that said, no, this isn't high enough. I'm going to go above that. And those towns were protected from the tsunami. So a lot of lessons there for us and for Japan. Yeah, but
Mexico, Taiwan, and Japan have early warning systems. How about us?
yeah, so question. So it is 11:30, so if you need to go, please feel free. There's a question about early warning systems for earthquakes. There are tsunami warning systems. We do have tsunami warning systems in place. Earthquake warning systems, though, in Japan, one of the reasons they didn't have as much damage from the earthquake is as soon as earthquake waves behave, there's sort of a primary wave that comes out first, and that causes some shaking, but not a lot. It's mostly picked up by seismometers, but it doesn't cause damage. And then the secondary waves are the ones that really kind of roll the ground and throw things around, and those are the ones that cause damage. And there's a time gap between the primary waves and the secondary waves, depending on how far away you are from the epicenter. So let's talk about Central Oregon as an example. If the next Cascade earthquake occurs, it's way off the coast of Oregon. We could have minutes that the primary waves will reach us, and we might not even feel them at all. And then it might be a minute or two before the damaging waves come. You can do a lot in a minute or two. Even in a few seconds, you can do a lot between those two waves. And so in Japan, as soon as primary waves are registered, instantly trains shut down. Elevators stop moving so that people don't get stuck in them. Warnings go out to hospitals, and if you're in surgery, everything's put down. And they're no one's going to cut into you when those waves start. Factories that are doing mass-produced, whatever, shut down. So all gas lines automatically shut off. The most damage that's generally caused after an earthquake is fires that break out from ruptured gas lines. And in Japan, those gas lines all just automatically close. So this is why there's very little damage from earthquakes in Japan. Taiwan, Mexico, other places on Earth have early earthquake warning systems. We do have one. That's the good news. For many years, I would talk about early earthquake warning systems, and we didn't have one. There was a beta system in San Francisco, but other than that, it hadn't gone out to the rest of the country. Now, Oregon, Washington, and California do have an early earthquake warning system. We're the only parts of the country that have that. But at least now you can get a warning on your phone. So you can go, it's called Shake Alert. So if you just go to USGS, US Geological Survey, and you look for Shake Alert, you can find all kinds of information, and you can get a warning on your phone. But that's about all you can do. We don't have it set up so that gas lines automatically shut down, trains don't stop moving, hospitals may or may not get a warning, and the surgeons may or may not put their tools down. BART, Bay Area Rapid Transit, is hooked up to this, and it will stop, but that's the only kind of example of that I know of that's automatic. So we have done a lot to get an early earthquake warning system here in the US. We still need to build on what we have, but at least now we have it, and that's really great news, and that's only in the last year or so, 2 years maybe. Yeah.
Japanese have been recording the tsunami incidents for the last 1,200 years. And it's actually written documentation that you could not necessarily go to any library, but you could go to a research facility and see when the last major tsunami was. And the pattern is every 350 years, which I find interesting that there's actually a pattern in the way the subduction characteristic takes place. But the fact of the matter is that the next one is late by 25 years, which means that are we going to have a major tsunami any moment or within 25 years? That's what's really difficult to forecast. But the fact of the matter is it's late and it will happen, and it's projected to be at 9.2 in terms of its impact in terms of the tsunami characteristic. The fact that we have no major cities in the upper Northwest actually on the coast. Seattle is protected by the distance that it's actually off of the coast that by the time the tsunami reaches Seattle, it may be probably not more than 3 to 4 feet of impact. Whereas the coastal city or cities, relatively small in scale, they'll be confronted by a 12-foot wall.
In some places, yeah, it really varies depending on the shape of the coastline. And yeah, Seattle's protected because there's the whole Puget Sound area. But other places along the coast, it can vary. In Oregon, it can vary from 20 feet to 100 feet. It just depends on the shape of the coastline. Shape of the coastline drastically impacts the height of the waves. Tsunamis themselves, I don't know of a scale for tsunamis for size, and the reason for that is that the size of the waves varies so much depending on the shape of the coastline. So there is no scale for a tsunami. You can't say we had a tsunami of X number when it's 100 feet in one place and 10 feet in another place. But earthquakes do have a scale, the magnitude scale. And so, yeah, the next Cascade earthquake could be anywhere between an 8 and a 9 plus. We don't know. And yeah, we're great at predicting where earthquakes will occur along faults. And we're great at predicting the size of the earthquake because we can measure the stress that's built up. And so we can correlate that to how much energy will be released. So we're great at predicting where along a fault, and we're great at predicting the size, but we can't predict when. So maybe one more question and then.
A little bit off, but I'll watch USGS and I'll see that there's a 6.9 in Japan. And the next day I'll look at that location and it's been downgraded to a 5.9. Why is that happening?
Yeah, interesting. The magnitude, that's the magnitude of the earthquake, and that's calculated based on a seismogram. So seismometers send out, a bunch of jagged lines representing the earthquake waves, and the magnitude is calculated entirely on those seismometers. And you need at least 3 readings from 3 different seismometers, but more is better. So it could be just that in the hours since from the first estimate of the magnitude to a couple hours later when more seismometers are getting data, that it just is tweaked just a little bit. But it's all based on the height of the amplitude, the height of those lines on a seismometer. That's how we calculate magnitude. And so I think just a little more data comes in and they hone that magnitude a little bit better. So it's not that there was bad information the first time, it's just there was less information to calculate it. And I think usually you probably don't see that change drastically. It probably just changes by a little bit. All right, so thanks again. I'm happy to answer more questions if you want to come up and ask questions. But